Welcome to the Op-Amp Labs. The first circuit is a comparator. Here it says, let Vn be a triangle wave at 4 volts peak to peak at 1 kilohertz. In this circuit, Vn is being compared to the voltage at pin 2, which is 0 volts. Compare Vout to Vin with an oscilloscope. This will require 2 scope probes. Draw the output signal on the graph provided. In this circuit, Vn is the triangle wave already shown on the graph. So that's your Vn signal. And the other input to the op-amp is connected to 0 volts. So therefore, your Vn is being compared to 0 volts. And this circuit, this op-amp circuit here, is a comparator. There is no form of feedback, so it's strictly operating as a comparator. And it's comparing Vn against 0 volts. So when your Vn is greater than 0, so when your Vn is greater than 0 volts, you're going to be in positive saturation. And when your Vn value is less than 0 volts, then you're going to be in negative saturation. And your Vn is at your Vn positive, and your 0 volts is at the input Vn negative. In looking at the signal that's being inputted, we are starting off already going above 0 volts. So therefore your Vn is greater than 0, and so the output is going to be in positive saturation. And when the output is at positive saturation, that's going to mean that you're at positive 10 volts. So therefore the output will already be starting up here. Now, as long as your Vn is greater than 0 volts, you will maintain positive saturation. Now, when the signal becomes negative, which is in this region right here, then you're going to be in negative saturation, and the reason for it is because your Vn now is greater than 0 volts, meaning that your Vn plus is less than your Vn negative. So therefore, right at the crossing of 0, that's where you're going to see it changing. So your output will switch right here, and it'll go to be a negative, and it'll stay negative until when? Well, until your Vn goes above 0 volts, which will happen right there again. And at that point, your output will go to positive saturation, and therefore will stay there until, again, the question is when? Well, when it crosses 0 volts again. And there it'll go to negative saturation once again, and it'll stay there until we go above 0 volts, which will happen right there. And draw that upwards like this, and there. So that's the output versus the input. So based on what's happening at the input, the output is shown. In the next circuit, we have a comparator with positive feedback. We are asked to calculate the upper threshold voltage and the lower threshold voltage values. Let Vn be a triangle wave at 4 volts peak to peak at 1 kilohertz, and to examine Vout to Vn using an oscilloscope. This again will require 2 scope probes, and draw the output signal on the graph provided. Before we are able to draw anything on the plot on the graph, we need to figure out what your VUT and VLT values are. For VUT, that's the upper threshold voltage, we need to assume that the output, that Vout, is in positive saturation. And then we need to figure out what the voltage is at that point right there. And since current does not flow into the input, therefore all the current really is flowing from Vout down to ground. So it's really a simple matter of using the voltage divider rule to figure out what the voltage is at, let's say, point A. Applying the voltage divider rule, then Vout is equal to, again, when we're solving for VUT, we're assuming positive saturation. So that's plus 10 volts times 1 kilo ohm over the sum of the resistances on the path, which is 11K. And the answer is 0.909 volts. Now this is positive because we're assuming positive saturation. To figure out the lower threshold voltage, we're assuming negative saturation. And again, it's a simple voltage divider equation. And the values, as far as the amplitude, is going to be the exact same thing, except you're going to end up with a negative 0.909 volts. Now, with that stated, or with those values solved, and we can jot those down for VUT, it's going to be a positive 0.909 volts, and for VLT, a negative 0.909 volts. What we can do next is to place those two crossing points, or if not, we could just draw a line. What we could do is to draw lines, which would be something like this. We could draw a line that's at 0.9, at positive 0.9 volts, which would be right about right there. And we could also draw another line at negative 0.9 volts, which would be somewhere about right there. Now the easiest for me would have been really just to put down dots for the crossing points. Now what I'm going to do is to show you what I mean by that is that I know that I'm going to have a change whenever my input, and the triangle wave is the signal at Vn. That's my input signal. And I know that I'm going to have a change at positive 0.9 volts and at negative 0.9 volts. So I can just indicate that with a dot. So I know that I'm going to have a change right here. And then I'll have a change right about here. Then another change right about there. Another change right about here. Another change right about there. So those are the points where I'm going to have a transition between the output being in positive saturation and making the transition to negative saturation, or vice versa. The question now is just, where is it going to start? Are we going to start off when we're drawing this from left to right on the plot? Are we going to start off in positive saturation or in negative saturation? So that is the question. Now, if we were to assume that we're in positive saturation, and let's put that here, if we were to assume that we're in positive saturation, we will have positive 10 volts right there. And so therefore we're going to have positive 0.909 volts at this junction right here. So therefore your Vin on the triangle wave, if we're starting off at 0 at Vn, because the triangle wave is starting at the origin, so therefore it's at 0 volts right now. So as your Vn is climbing up, because the triangle wave, that first part there starting at the origin, is ramping up, so the Vn is going to increase, but it's going to have to go above positive 0.909 to cause the Vn negative to be greater than your Vn positive. When your Vn negative input becomes greater than your Vn positive input, that's when you're going to negative saturation. So therefore, you must inherently be starting out in positive saturation. So if you're starting out in positive saturation, you'd be up here. And then at this crossing point right there, you would see the transition to negative saturation. And you'd stay at negative saturation until the next crossing point, which therefore you would go up like this. And then you would stay in positive saturation until the next crossing point, which would be right there. And then you would stay in negative saturation until the next crossing point, which would be right there. And then finally, you would switch again at the next transition point, which would be right there. So again, the thing to figure out is just where you're starting out at. And again, if you assume positive saturation, you can figure out what the value is that you're going to be comparing against, which is at the junction, which is where your positive 0.909 volts are. And therefore, your Vn has to start off at 0 volts because you're starting at the origin on the triangle wave. And you're going to have to go above your positive 0.909 0.909 volts in order to cause the Vn negative to become greater than your Vn positive. And again, when your Vn negative input becomes greater than your Vn positive, that's when you're going to go into negative saturation. That means that therefore you must be starting out in positive saturation, because when your Vn negative becomes greater than your Vn positive, you're going to go into negative saturation. So inherently, again, you must be starting out in positive saturation. So that's what the result would be for this lab here. Our next circuit is a voltage follower. And for this one, it's asking us to let Vn be a triangle wave that is 4 volts peak to peak at 1 kilohertz, and to compare Vout to Vn with an oscilloscope. This will require 2 scope probes, and draw the output signal on the graph provided. In this circuit, we do have a voltage follower. And for a voltage follower, we know that we have a voltage gain that's equal to 1. That's always. A voltage follower always has a gain of 1. And also, it's a non-inverting input. So basically, what it means is your Vout is equal to your Vin. So it doesn't amplify it, it doesn't really change it, so it's just a buffer amplifier. So therefore, what you would expect to see then is really that your Vout is doing the exact same thing as your Vn. So really, it's just a tracing over of the input signal. That's what you would expect to see at your output. So your output is equal to your input. Now, one of the ways that you can tell that it is a voltage follower is because your output is directly connected to your inverting input. There is not a resistor there or anything of that sort. It's just a straight shot. All right, it's just a short right there. And that's how you can tell that it's a voltage follower, a buffer amplifier, because of that feedback loop that is there, and because you're taking your Vn in the Vn positive pin. This next circuit is a non-inverting amplifier. We're asked to calculate the gain for the non-inverting amplifier shown, and to let Vn be a triangle wave with 1 volt peak to peak at 4 kilohertz, and compare your Vout to Vn with an oscilloscope. This will require 2 scope probes. Draw the output signal on the graph provided. And did you see what you expected? So let's do this one. For this non-inverting amplifier, one of the things that we should figure out is what is the gain? What is the gain of the amplifier? Well, for a non-inverting amplifier, your voltage gain is equal to R2 plus R1 over R1, with this resistor connected to ground being R1 and this other resistor being R2. So therefore, we have something like 10k ohm plus 5.6 k ohm divided by 5.6 k ohm, which gives us a voltage gain of 2.78. In analyzing the input signal, which is a 1 volt peak to peak triangle wave, since it's 1 volt peak to peak, I know that the height of the triangle wave right there is at positive 0.5 volts. And I know that on the negative side, we're at negative 0.5 volts. So once this peak is reached at the input, we know that the output should be, we can come up with an equation for that. The V peak is equal to your plus 0.5 volts times your voltage gain, which is 2.78. Therefore, the signal, as far as the output signal, will peak at 1.39 volts. So what I could do then is to draw my peak points per se. So at 1.39, I know I'm going to have a peak right about right here, and I'm going to have a peak right about right there, and one right here, and one about right there, and one about right here, and one about right there, more like about right there, and this one would be more about like right there. So now to draw the output signal, it would do something like this. So it's just an amplification. Again, it's a non-inverting amplifier. So that's what it would appear like. Something like that. I went ahead and changed the circuit for the non-inverting amplifier a bit. So I'd like to go ahead and do this one now. This is actually what you would find in the updated lab. So again, we're on the non-inverting amplifier. In this case, what I did was I changed the values of R1 and R2 just to make it a little bit easier to draw, to plot it out. So let's do this one. So again, we do have the non-inverting amplifier, and one of the first things to solve for is the voltage gain. So as we stated, this resistor is R2, this one is R1, and so A sub V is equal to R2 plus R1 divided by R1. So therefore we have our 10K plus our 2K ohm, and we're going to divide that by 2K. So that gives us a result of 12K ohm over 2K ohm. And since the actual units will cancel out, and then it's just really just 12 divided by 2, we have a gain of 6. Now, just like on the previous example for the non-inverting amplifier, we see that the peak of the triangle wave is on the positive side at 0.5 volts, positive 0.5 volts, and on the negative side, right there, we're at negative 0.5 volts. So therefore, to figure out what the peaks are of the triangle waves, what I'm going to do is to just figure out what V peak will actually be. So V peak, as far as your peak output, will be, say, 0.5 volts times 6, which is equal to 3 volts. So since this is a non-inverting amplifier with a gain of 6, I know that on the positive side, it's going to peak out at positive 3 volts, and then on the negative side, it's going to peak at negative 3 volts. So the easiest thing to do is just to place dots. So that's what I will do. I will place dots where the peaks will be. On the positive side, where the triangle peaks, it's going to peak right about right there. On the negative side, we're going to have a peak right about right here. And on the positive side again, we'll peak right about right here. Negative side, right about there. Positive side will be peaking right about right here. Negative side will be peaking right there. And on the positive side again, right about there. And on the negative side, we would be right about right here again. Now all I need to do is to connect the peaks, and of course, when the triangle wave is at 0 volts, therefore 0 times your gain is still 0. So we would expect it to be crossing right about right there. So we're going to have a rise, we're going to have that, and basically it's connecting those dots together. So what you would be aiming for is when your Vin is equal to 0 volts, you know that your V out has to also equal 0 volts, because again, your Vin times your gain is equal to your V out, and if your Vin is equal to 0 volts, then V out is equal to your Vin times your voltage gain. So therefore 0 times your voltage gain of 6, you know that your V out will be equal to 0 volts. So at the crossing points, you know that the output will be crossing 0 as well. And since it's non-inverting, when it peaks in the positive fashion, you know that your output is going to be peaking in a positive fashion as well, and vice versa. The next amplifier to look at is the inverting amplifier. And we're asked to figure out the gain for the circuit shown, and let Vin be a triangle wave with 1 volt peak to peak at 4 kilohertz, and compare Vout to Vin with an oscilloscope, and this will require 2 scope probes, and we're asked to draw the output signal on the graph provided. So let's do this. For the inverting amplifier, we have the gain equation where our A sub V is equal to negative RF over Rn. So our feedback resistance is 10 kilo ohms. Your Rn value is 5.6 k ohm. So let's figure out what the gain is. The gain is 1.78. Now this of course is a negative 1.78. Since this is a fairly small gain, and we're not going to really be able to plot it all that well on here, I think the best thing to do is to change the values of our circuit to better illustrate it. So let me do that, and we'll restart this again. I have since changed the circuit to what you see here in the lab, so this is now what is in the updated lab. This will allow us to be able to see a better response on the output, something that's just a little bit larger than what the previous circuit would actually have at its output. So one of the first things again is to figure out what the voltage gain is. So A sub V is equal to negative RF over Rn. So we have negative 10 kilo ohms over 1 kilo ohm. So the result is that we have a gain of negative 10. Now as far as the signal at Vn, well, that's a 1 volt peak to peak at 4 kilohertz. So we know that the peak of the wave will actually be at positive 0.5 volts on the positive side, and on the negative side it's going to peak at a negative 0.5 volts. So the easiest way to plot this is just to figure out where the peak points are and then draw lines between those points. So if we take a look at the starting point, we know that if the Vn is 0, so even, it doesn't matter what the gain is, but if your input is 0, 0 times any gain will still be 0. So we know that the starting point, of course, was going to be the origin. So that's our starting point, and you see a blue dot right there. Now, when the input reaches a peak of positive 0.5 volts, positive 0.5 volts times negative 10 is going to give you negative 5 volts. So we're going to have a point right about right there. And then again, when the input is at 0 volts, when it's crossing right here, your output will be 0 volts. Then when this input signal reaches a negative peak, a negative 0.5 volts, your output will be at a positive 0.5 volts, which will be up here, right about there. And again, when the input signal is at 0 volts, right about right there, the output's going to be 0 volts as well. Then on the positive peak again at positive 0.5 volts, we're going to have the output be at negative 0.5 volts, which would be right about right there. And again, we're going to have your Vout be 0. Again, the thing is to put the points down and then to draw lines between those points. So we know whenever the input, your Vin signal, is at 0 volts, you know your output's going to be at 0 volts as well. So I know I'm going to be right there, right here, and right here when I'm going to have an output of 0 volts. Now the question is just basically where the peaks are. Well, when we peak out at a negative 0.5 volts, we're going to be at a positive 5 volts at the output, because that's the input times the gain, so we'll be here. And then when the signal peaks at a positive 0.5 volts, we're going to be at a negative 0.5 volts, which will be right down here. And then at negative 0.5 volts, we're going to have a positive 5 volt output, which will be right about right there. And then when the signal again peaks at a positive 0.5 volts, we're going to have a negative 5 volt output, right about right there. And of course we have a crossing point right there as well. So now all we have to do is to connect these dots together. So we're going to have something that looks like this right here. Then from here we're going to go right there. Then from right there to right here. Then from right here to right there. From there to there. From there to there. From there to there. From there to there. So that's what the output would appear like, and this is again is for an inverting amplifier. So again, when the signal is positive, your output is going to be negative. So when the input peaks at a positive 0.5 volts, then your output is going to be that positive 0.5 volts times a gain of negative 10, which therefore becomes a negative 5 volts on your Vout. And that's what the graph here shows. This last particular lab was creating a non-inverting amplifier but with a single voltage supply. And what I want to do is just basically make note of the circuit. So let me go ahead and put this up so we can analyze it a bit further. So as stated, this is a non-inverting amplifier. We have what we would call our R2 value here. The 5.6K is our R1 value. And this in most cases was going to be reference to ground. But because we are working off of a single supply, you can see here we have VCC, but then we have ground on what would have been the VEE. Therefore, we need to shift the virtual ground to be 1/2 of VCC. So this point right here, and I'll call this well, I'll just draw it, a large green dot right there. That point right there is supposed to be connected to ground if we were using a bipolar power supply. But because we're using a single supply, that point needs to have 1/2 of VCC on it. And how we do that is by this circuit right here. This is our virtual ground circuit. And what it does, again, it splits VCC in half. You can see a voltage divider circuit right here comprised of two 100k ohm resistors in series. That's going to split VCC in half. So let's just say that VCC was equal to positive 9 volts. Well, therefore, if VCC is equal to positive 9 volts, this halfway point is going to be equal to positive 4.5 volts. And since the amplifier that's used to create the virtual ground is a voltage follower, a buffer amplifier, that means that the gain is going to be 1. That means I'm going to see positive 4.5 volts at the output. And again, that's positive 4.5 volts. Let me change that a bit. Let me just draw an arrow right there. That point is positive 4.5 volts. And with that arrangement, we're able to make this circuit operate as a non-inverting amplifier. Now please note that we did use a bleed resistor right there, and we did have input caps, or an input cap I should say, and an output cap as well. So this particular amplifier will only work with AC, but we did have to incorporate a bleed resistor, which allows a small amount of current to bias the transistors at the front end. And that concludes the labs for the op amps.